Hello, 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 hello. Hello. Good evening. We'll continue our discussion on subgroups. And last time we saw two tests to find out whether a subset of a group is a subgroup or not. First one was the one-step subgroup test, in which if H is a non-empty subset of a group G, then as long as for all AB in H, AB inverse is also in H, then H will be a subgroup of G. And the two-step subgroup test was that the H is a subset of a group G and it is non-empty and it follows closure. That is, if A and B are in H, AB is in H, and every element has an inverse in H. That is, if A is in H, A inverse is in H. Then we need not look for the identity. These conditions will guarantee associativity and the existence of identity. So we just check closure and existence of inverse. And if that holds, then H is a subgroup of E. We saw some examples uh, and showed how the test can be used when the subgroup is specified using a property of the element. Then if A and B have that property, you can check if AB inverse has the same property in the case of the first test, or you can check whether AB has that property and A inverse has the property in the second test. For finite subgroups, the two-step subgroup test actually can be reduced to again a one-step subgroup test. So for a finite group, let H be a non-empty finite subset. So here the group does not need to be finite. Of course, if the group is finite, any subset of that group will also be finite. And by saying by the group is finite or infinite, what we mean is the order of the group is infinite or finite. So let H be a non-empty finite subset of a group G. So H is finite, then if H is closed under the operation of G, then H is a subgroup of G. So now in the two-step subgroup test, we had to show closure and the existence of inverse. But here I am saying if the set is finite, if the subset is finite, then I don't need to show that an inverse exists. That means if you show that for a finite subset H, each element will always have an inverse within the set, then that means I don't need to check for the inverse also, just closure is enough. So can you show that? No, not the that one. Here we are saying only closure. A, B is in H. Yes. Yeah, associativity is already directly follows from the associativity of the operation in G. Then, if we show that every element has an inverse and it is closed, then obviously identity will be there since the set is non-empty. So we don't have to care about the identity also. In the two-step subgroup test, we cared about closure and existence of inverse. What I am saying is, in a finite set, closure will assure that inverse exists. How do I show that? How do I show that from closure we can prove that an inverse will always exist within the set? First thing that we can uh, get out of the way is that suppose uh, so in view of um, two-step subgroup test, we only need to prove that if H is closed, then for all A in H, A inverse belongs to H. That's what we have to show. Now we can split it into two parts. If A is the identity element, then its inverse is the identity element. A inverse is equal to E is equal to A. This is in H. So we don't need to show that the inverse of the identity is in the set H. That is always true. Then we can assume, suppose A is not equal to E. Then the way we use finiteness of the set is this way. We take all the powers of A. So we consider the sequence A square, etc. By closure, all these elements are in H. Because I have assumed that H is closed. Then I am showing that if H is closed and H is finite, then every element has an inverse. So by closure, all the elements A square, A cube are all in H. But H is finite. So A power I is equal to A power J for some I and J. Because if each of the powers of A was different, then there would be an infinite number of elements, distinct powers of A, which would all belong to H. That would mean that H is in, H has infinite order. That is not true. H is finite. So since A is in H, A square, A cube, A power 4, everything, all the powers of A are also in H. But each of them, if they are distinct, that will mean that there are infinite elements in H. So they can't all be distinct. So at least two of them should be the same. And without loss of generality, let I be greater than J. I'll call the bigger power I, the smaller power J. Now A power I into, if A power I is equal to A power J, then A power I into A power minus J is equal to A power J into A power minus J is equal to A power J minus J equal to A power 0, it is E. So A power I minus J is equal to E. Then we can write A into A power I minus J minus 1 is equal to, then A power I minus J minus 1 is the inverse of A. Now we have to make sure that this A power I minus J minus 1 is not some trivial element. It's not, it makes sense. And it is some non-negative power of A. Because I was greater than J, I minus J is greater than or equal to 1. And I minus J minus 1 is greater than or equal to 0. So it is a non-negative power of A. And all non-negative powers of A belong to H by closure. So this A power I minus J minus 1 is one of the elements of A square, etc. Or it if it is E, then that would mean that A is equal to E, which is Not the case because we had assumed that A is not in. We had assumed suppose A is not in. So A power I minus J minus 1 is some power, positive power of A. And since A is in H, all positive powers of A are in H. So A power I minus J minus 1 is in H. And that is the inverse of A. Any difficulty in this? Okay. That's it for the subgroup tests. Those are the only ones we will study. Then we'll see some important examples of subgroups. Before that, we'll give some notation. For any element A in a group G, we define this to be the set of all A power n in Z. That is the set of all powers of A, including the negative powers and the positive powers. So this is A power 0, which is the identity. So A power 0, we define it to be the identity, and by A inverse, we mean simply A inverse. A power minus 2 is actually A inverse square. This is A inverse cubed. So the set of all powers of A, integer powers of A, this is denoted by this angular kind of less than or equal to symbol uh, A within those type of brackets. And we'll show that this is actually a subgroup. Can we show this? First, we have to show it is non-empty. Yeah. A power 0 equals C belongs to this set. So for, clo- for closure, we pick two elements and show that their product should is in the set. Yeah. So it is a subgroup. It is a subgroup of whatever group A is from. Now we have a name for this, and it is also difficult to simply. Uh, yeah, we need a name for this. The symbol is notation to write it down, but how do you say it? And for that, we call this subgroup A is called the cyclic subgroup of G generated by A. Also, if it happens that the case that G is equal to the subgroup generated, cyclic subgroup generated by A, we say that the group G is cyclic. Cyclic, however you want to say, up to you. And we say A is a generator of G. Now, one thing to note here is that I said A is a generator of G. So the same group, the cyclic group, may have many generators. So if a group is cyclic, it does not mean that there is only one generator. I'll give examples. I'll give examples. Huh. Oh yes, yes. A inverse would be a generator, and some other powers of A would also be generated. Yeah, that will depend on the order of G and the order of A, order of G, which is the order of A in the case it is a cyclic group. It will depend on the order of that element. So here you have to note that when defining these things, we didn't really say that A has to have finite order. If A has infinite order, that is also fine. The subgroup will be of infinite order. That's not. But I'll give examples. If it is finite, though the list has infinite powers of A, if you take it as a set, then the powers might, many powers might be identical, and you might only have finitely many elements. Also, if the group is cyclic, then A power I into A power J is A power I plus J. But addition is commutative in integers, so this can also be written as A power J plus I. So this can again can be written as A power J times A power I. So A power I times A power J is equal to A power J times A power I for any I and J. Therefore, every cyclic group is abelian. Now we'll look at some examples. Consider the group U10, which is all the numbers, positive numbers less than 10 and relatively prime to 10. This is nothing but 1, 3, 7, and 9. The operation is mod 10 multiplication. Now consider the subgroup generated by 3. Contains all the powers of 3. 3 power 1 is 3. 3 square is 9. 3 cube is 7. 3 power 4 is 1. Yes. So 3 is a generator of U10. No. Yeah. We have defined a cyclic group to be a group that is generated by some element in the group. And we say G is generated by A, it is understood that A is an element of G. And 7 power 7 is also same. 9 power 1 is 7, 7 square is 9, 7 cube is 3, 7 power 4 is 1. What about 9? 9 power 1 is 9, 9 square is 1. And 9 inverse is 9 itself. So all the powers, the subgroup generated by 9 is simply 1 and 9. Yes, yes, yes. So that is how we define the order of an element. That is why we defined it in that way. Because the order of the element, so the order of the element is equal to the order of the subgroup generated by the element. We'll show that later. So if you get a power m is equal to 1 for some m that is less than the order of the group, that means that element does not generate the group. Only elements with order n will generate a group of size n. Now here 9 has order 2, so it won't generate a group of order 4. So 3 and 7 are generators. Like I said, the same group has two generators, so it can have more than one generator. But not all elements of the group need to be, I mean, not all elements have to be generators. 9 is not a generator of this group. So to call it cyclic, we just need one element which generates it. Whether the rest of the elements generate it or not, that does not matter. And this is only useful if not all elements are, not all groups are cyclic. If all groups are cyclic, then there is no point in differentiating between cyclic and non-cyclic groups. One simple example is the symmetry group. We will come to that later. Just in Z10, the subgroup generated by 2 is 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10, which is 0 in Z10. When we say Z10, it's mod 10 addition because 10 is not a prime number and Z10 also contains 0. So it won't be a group under multiplication. So what, yeah, why I did this example is because since it's an additive group, here the subgroup generated by A is instead of uh, powers of A, it's multiples of A. And this multiple of A means that you add A and there are n terms in the expression, in the sum. So A added to itself, there are n terms in the sum. That is how the subgroup generated by A is defined in additive notation. So now we can see that Z was a group under addition. What is the subgroup generated by 1? Z addition only, right? Z is not a group under multiplication. Yes. So you have this is the group Na for n in Z. So you have minus 3 times 1, minus 2 times 1, minus 1 times 1, 0 times 1, 1 times 1, etc. But minus 3 times 1 is by definition 3 times minus 1, which is minus 1 plus minus 1 plus minus 1, which is minus 3. And 0 times 1 is by definition 0. So this is simply the group minus 3 minus 2 minus 1 0 1 2 3, which is Z itself. What about the subgroup generated by minus 1? What is this subgroup? Yes, this is also good because minus 3 times minus 1 simply means 3 times inverse of minus 1, which is nothing but inverse of minus 1 is 1 in addition. So 3 times 1 is 1 plus 1 plus 1 is 3. So this will be 3, 2, 1, 0, minus 1, minus 2, minus 3, which is same as Z. Does Z have any other generators under addition? Are there any other generators of this group? Yes. We can't get those if you take an integer a, you can't generate any integer less than that, and any positive integer that less than that. So you can't generate a minus 1, a minus 2. using A. So it can't be B. So if A is not 1 or minus 1, you can't generate 1 from it. No multiple of a integer that is not 1 or minus 1 will be equal to 1. So since you can't get 1 itself, then it cannot be the entire set of integers. Actually, there is one interesting thing about the subgroups of integers which are useful. So some of the things that I had shown regarding the greatest common divisor, I had given one kind of proof. Those things can be proved by using the next fact or theorem that I will show. Before that, I will show something else. We'll take this as a lemma. For any element integer a in z, az, which is defined as a times n in z, is a subgroup of z. For example, 2z is the multiples of 2. Right? Minus 4, minus 2, 0, 2, 4, etc. We are considering addition, so 0 is the identity. 3z is all multiples of 3. Minus 6, minus 3, 0, 3, 6, etc. That will be a subgroup. First thing is that 0 times a is equal to 0. So az is non-empty and it also has the identity. Then consider two elements of az, am and an, for some integers m and n. Am plus an is simply equal to a times n plus n. That's from the properties of integers. And since m and n are integers, m plus n belongs to z. The sum of two integers is an integer. So am plus an is also a multiple of a. So this belongs to the set az. Well, this is actually this theorem here. What was it? The subgroup generated by A is a subgroup, right? It's the same but in additive notation. For a specific example, I'm doing this. That's all for integers. And a times minus m belongs to az, and a times minus m is equal to minus of a. So az is a subgroup of z. So you take an integer and take all its multiples. That is a subgroup generated by that integer. And as we saw, the subgroup generated by an element of a group is a subgroup. I mean, uh, set generated by the element of a group is a subgroup. So the set of all multiples of A is a subgroup for any integer A. But the interesting fact here is that every subgroup is of this form. There are no other subgroups of Z. Every subgroup of Z is of the form AZ for some non-negative integer A in Z. Can you show this? But then you can't simply say that if it is not of the form AZ, then I'll pick two elements. There's some won't be in the group. So that you can't simply say that, no? Yes, you have to prove that. Instead of that, what we'll do is first we'll get rid of the empty. We'll get rid of the trivial subgroup. We have to show that any subgroup H is of the form AZ. So we'll say let H be a subgroup of Z. If H is simply the trivial subgroup, then H is 0Z, which is simply 0 times n in Z. All multiples of 0 are simply 0. So H can be written as 0Z. And the theorem claims that for some non-negative integer A, the subgroup should be expressible in the form AZ. So as long as if H is a trivial subgroup, H is equal to 0Z and we are done. Suppose H is not the trivial subgroup. Suppose that H is not equal to 0. What does that mean? That means that H contains an integer n in Z because H is a subgroup of Z. It can contain only integers. N not equal to 0. If n is less than 0, then since H is a subgroup, its additive inverse also belongs in the subgroup. Minus n belongs to H. Now minus n is greater than 0. So we have shown that if H contains an integer that is not 0, then H will contain a positive integer which is not 0. So it's not possible that you have a subgroup containing only negative integers because the inverse of a negative integer is a positive integer, and the subgroup will contain the inverse of every element inside it. So the only subgroup that does not contain a positive integer is the trivial subgroup. We have already gotten rid of the trivial subgroup case. So H contains at least one positive integer. It contains at least one positive integer. Now let A be the smallest positive integer. Contained in H. So in the preliminaries, we had shown that for any set of positive integers, there is a smallest element. We had taken that as an axiom, which is the axiom of well ordering, the well ordering principle. So any set of positive integers has a smallest element. Since H has one positive integer, there is one smallest positive integer. If we take the set of all positive integers in H, there will be some element which is the smallest element and or smallest positive element. We'll call that A. Now our claim is H is equal to AZ. If we have a subgroup of Z that is not the trivial subgroup, then it must contain positive integers because if it has a positive integer, fine. If it has a negative integer, then its inverse is a positive integer. And since H is a subgroup, that must be in H. So H always contains positive integers. And if we take the smallest positive integer in H and call it A, then H is simply AZ. Now we have to prove that. And when we want to prove two sets are equal, the most common form of doing that is showing that if A is equal to B, if we want to show A is equal to B, we show that A is a subset of B and B is a subset of A. Then that is only possible if A is equal to B. One side is very easy. A belongs to A belongs to H, so any multiple AN belongs to H for all n in Z. That is by closure. Since A is in H, by closure AN belongs to H. But AN, the set of all AN is nothing but AZ. Okay. To show X is a subset of Y, you have to show that if X is in X, then X is in Y. We'll do that. Consider X in AZ, then X is AN for some n in Z. But since it is integers, AN and NA both are the same. And since it is integers, NA is nothing but A added n times. This belongs to H by closure. So X is in AZ implies X is in H. So AZ is a subset of H. That is, if A is in H, all multiples of A are in H. And AZ is the set of all multiples of it. So AZ is a subset of H. That direction is clear, no? Now we have to show the other direction, which is a bit harder. To show the other direction, what we have to do, we have to assume that, suppose B belongs to H, we have to show that B belongs to AZ. So this is to show H is a subset of AZ. For any B in H, we have to show that B belongs to AZ. That is, we have to show B is equal to A times N for some integer N in Z. To do that, what we do is, by choice of A, how did we choose A? We said A is the smallest positive integer in H. First, we'll do for the case when B is a positive integer. Okay. Let B greater than 0, B be an element of H. Now, by choice of A is the smallest positive integer in H, so B must be greater than or equal to A. Now you can divide B by A and write B is equal to AQ plus R, where R is greater than or equal to 0 less than the divisor A. This we know from the Euclidean division algorithm. Now R is B plus minus Q times A, or you can write the Q times minus A. Okay. Now we have B is an element of H, right? Let B greater than 0 be an element of H. We also have A is an element of H. Right? A was the smallest positive integer in H. That's how we chose A. Since A is an element of H and H is a subgroup, minus A belongs to H. Since minus A belongs to H, Q times minus A belongs to H. Because Q times minus A is nothing but if Q is positive, it's A minus A added Q times. If Q is negative, it's A added Q times. Since both A and minus A are in H, Q times A and Q times minus A are both in H. Since Q times minus A is in H and B is in H, and H is a subgroup, R, which is B plus Q times minus A, is in H. But from the division algorithm, R is greater than or equal to 0 and less than A. If R is a positive number, that is a contradiction, right? Why is that? Why can R not be a positive number? R is greater than or equal to 0, less than A, right? I am saying R has to be 0. Why can R not be positive? I just I just showed that R is an element of H. If R is positive, what is the issue? What is A? No, it is not just any element. What is the specific? How did I choose A? So we showed that H has positive integers in it. If H is not trivial, then we said since it has positive integers, it has the smallest positive integer because of well ordering principle. Any set of positive integers you can arrange in ascending order, and the first element will be the smallest, right? We chose that to be A. A is the smallest positive integer in the subgroup H. Then H is equal to AZ. So H, any subgroup H is generated by its smallest positive integer in that subgroup, is what I was claiming. To show that, we showed that since A is in H, all multiples of A are in H because of closure. And all multiples of A is simply the set AZ. So all elements of AZ are in H. So AZ is a subset of H. That is one direction. And if I show that H is also a subset of AZ, that would mean that H is equal to AZ. Because if A is a subset of B and B is a subset of A, then A is equal to B. To show that H is a subset of AZ, I took an arbitrary element in H. I called it B. Say initially for case 1, let B be a positive number. Since B is a positive number and A is the smallest positive number in H, B is also an element of H. Then B must be greater or equal to A. So A is the smallest positive integer in H. Then if one number is greater or equal to the other, you can divide the larger number by the smaller number. Right? So divide B by A. You will get B is equal to AQ plus R for some quotient Q and remainder R. And by division algorithm, we know that the remainder is some number that is greater than or equal to 0. R is greater than or equal to 0 or less than A. Now, if B is AQ plus R is B plus minus of AQ, which is nothing but B plus Q times minus A. Now, B was an element of H, A is an element of H, so minus A is an element of H, then Q is a multiple of minus A, which will also be an element of H by closure. So B is an element of H and Q times minus A is an element of H, which means their sum is an element of H by closure. The sum is nothing but R. R is B plus Q into minus A. So R is in H. Now I am saying R must be equal to 0. Why can here I have underlined, right? R is greater than or equal to 0, less than A. But R must be equal to 0. It cannot be a number with greater than 0 and less than A. Why is that? So what? Okay. So what? Yes, that is my aim. But why is R equal to 0? Suppose suppose A is 4. Why can't R be equal to 3? What is the problem? Why should R be equal to 0? Yeah, I just showed that initially we chose A from H. So 4 is in H. Then I showed that R is in H. So 3 is also in H. Then I said initially when I was choosing A, that's the smallest positive integer in H. I said 4 is the smallest positive integer in H. Does that make sense? If 4 is smallest positive integer in H, can 3 be in H? Yes. So R cannot be a positive number. If it is a positive number, it is less than A that we know. If it is a positive number, then that would mean that R was actually the smallest integer. We chose wrong. A could not have been the smallest integer. So R must be 0. By definition, A is the smallest integer in positive integer in H. And R is also an element of H, which is less than A. If R is positive, that would have been the smallest positive integer in H, which is not possible by definition of A. So R must be equal to 0. If R is equal to 0, then B is equal to A times Q. A times Q is a multiple of A, so it belongs to AZ. So B belongs to AZ. What we have shown is that if B is in H and B is greater than 0, then B belongs to AZ. If B is less than 0, then minus b is greater than 0. So minus b is equal to aq for some q in Z. Right? B here was any arbitrary positive element of H. And since B is in H, minus B is also in H, and minus B is a positive arbitrary element of H. So minus B can also be written as AQ for some Q in Z, which means that B is simply A times minus Q. And this belongs to AZ. Whether B is positive or negative, it is a member of AZ. What we have shown is that if B is in H, then B belongs to AZ, which means by definition H is a subset of AZ. AZ is a subset of H, then H is a subset of AZ. So H is equal to AZ. Okay, you can go through the proof again later, no problem. The main takeaway is that every subgroup of Z can be written as multiples of A. That can be written as AZ, where A is the smallest positive integer in Z. Of course, that is disregarding the trivial subgroup. If it if the subgroup is just this group containing 0, then it can be written as 0Z. So, okay, then you can say that every subgroup of Z is of the form AZ for some non-negative integer A. If it's the trivial subgroup, A is 0. If it's not the trivial subgroup, then A is the smallest positive integer in the subgroup. This is not true for the groups in general. Groups in general might not have this kind of structure for all subgroups. There might not be one particular structure that you can say that all subgroups of a group have. Or only for integers, all subgroups must be of the form AZ. Okay, then we'll go back to this subgroup generated by A. We'll go back to the earlier discussion. So it is useful to think of the subgroup generated by A as the smallest subgroup of G that contains A. It contains the subgroup generated that contains A. So it contains the subgroup generated by A also. That is, if H is a subgroup of G and A belongs to H, then the subgroup of generated by A is a subset or equal to H. So any other subgroup that contains A will also contain the subgroup generated by A. So this is the smallest subgroup that contains A. You can extend that notion to a set of elements. So for a collection S of elements of V, you can define this subgroup with the property that this subgroup, whatever it is, contains all the elements in the set S. And if H is some other subgroup of G that contains all the elements of the set S, then H also contains the subgroup generated by S. So by that definition, the subgroup generated by S is the smallest subgroup of G that contains all the elements of S. And we call this set as the subgroup generated by S. It's not it's not just the union. You should also have 1, 5, and 7, the subgroup generated by that will have all, it will contain 1, 5, and 7. That means by closure, it will also contain all multiples of 1, 5, and 7. Then it will also contain sums of multiples of 1, 5, and 7. So it can contain 1 plus, it should contain 1 plus 5 also, 5 plus 7, and 1 plus 7. And the multiples of all those elements. Then the sum of those again. Okay. So this is called the Gaussian integers. So this is the set A plus IB, where A and B are integers, and I square is minus 1. So I is the square root of minus 1 from complex numbers. This set is called the set of Gaussian integers, and it is generated by 1 and I. You can verify that this set of Gaussian integers is a subgroup under addition. So under addition, a plus ib plus c plus id is a plus c plus I into b plus d. If a, b, c, d are all integers, a plus c is an integer and b plus d is an integer. So it is of the form an integer plus I times an integer. So it is in the group of Gaussian integers. Then 0 plus I 0, which is equal to 0, is the identity element. And the inverse, additive inverse of any number a plus ib is minus a plus I times minus b. And if a and b are integers, minus a and minus b are also integers. So minus a plus I times minus b is also in the set of Gaussian integers. Associativity similarly follows. You can check that associativity also. So this is a group, right? And it is a subgroup of the group of complex numbers. Complex numbers, a plus is set of all a plus ib where a and b are real. If I restrict my a and b to be the set of integers, then this is a subset of complex numbers, right? And it is a subgroup under the same addition operation in complex numbers. This addition is same as addition in complex numbers. Only restriction is that we are restricting a and b to integers instead of real numbers. So this is a subgroup of the set of complex numbers under complex number addition. This will be generated by the set 1 and I. So this set 1 belongs to the set generated by 1 and I, right? So 1 plus 1, which is 2, belongs to the set generated by 1 and I. 1 plus 1, which is 3, belongs to. And 0 times 1, which is 1, belongs to. So it contains all multiples of 1, right? So it contains all integers. Now it also contains I. So it must contain I plus I, which is 2I. It must contain minus I. So it contains minus I plus minus I, which is minus 2I. So it also contains all multiples of I. It must contain them. So A belongs to the set generated by 1 and I for all A in Z. B belongs to the set generated by 1 and I for all. So B I times B or BI for all b in Z. Every multiple of I. Since A and Bi belong to that set, A plus Bi belongs to for all integers A and B. So this is nothing but the set of Gaussian integers. Now the thing is, the set of Gaussian integers here is generated by 1 and I, right? So it is generated by the set S. So it contains the set S, which is 1 and I. If you take any subgroup that contains 1 and I, it must contain all multiples of 1 and all multiples of I, right? So it must also contain the sum of multiples of 1 and sum of multiples of I. So it must contain the set of Gaussian integers. So if there is some other subgroup of complex numbers that contains 1 and I, must also contain the entire set of Gaussian integers. So we call this G, and G is a subgroup of complex numbers. If H is a subgroup of complex numbers and 1 comma I, 1 belongs to H, I belongs to H. Or you can say the set 1 comma I is a subset of H. Then G is a subgroup of H. For example, the complex numbers itself is a subgroup of the set of complex numbers, right? And it contains 1 and I. So it must contain the Gaussian integers entirely. Similarly, if there is some other subgroup that is not the complex numbers, but it contains 1 and I, it must contain the entire set of Gaussian integers. So the set of Gaussian integers is the smallest subgroup of the complex numbers with the least number of elements, you could say, such that 1 and I are contained in it. So that is how it will go for 2 elements. For 3 elements, you will have to take all multiples. What will happen in the case of 3 elements? Like you said, 1, 5, and 7, a subgroup that contains this, right? This will contain, so one, if it contains 1, it should contain all multiples of 1, right? So it will be just be the set of integers. So we could try by taking out 5 and 7. Taking out 1 and introducing some other number, maybe 5, 6, 7. So this should contain 5 and all multiples of 5. It contains 5z, contains 6 and all multiples of 6. It contains 7 and all multiples of 7. But but again the thing is it should contain 11, should contain 11 and all multiples also. Should contain 13 and all multiples. Should contain 12 and all multiples. But again the thing is since it contains 7 and it contains 6, it should contain minus 6. And it will contain minus 6 plus 7, which is 1. So this will simply be the set of integers again. uh, yes, yes. But the thing is, since it is a subgroup of integers, now that is where that earlier theorem becomes useful. Since it is a subgroup of integers, regardless of what it is, it will be of the form dz for some integer z. So you can simply find the smallest positive integer in this set. So in this case, it turns out to be 1. So the set is 1z. But if there was some other integer t, for example, if you take multiples of the same, if you take relatively prime numbers, what happens is you can always, if you just take any two relatively prime numbers, right, a and b, so if you take subgroups of z generated by, if a and b are relatively prime, then we saw one theorem in the preliminaries that you can always write, then GCD of a comma b is 1, but GCD is the smallest positive number that you can write in the form of as plus bt. So you can always write as plus bt is equal to 1 for some integers s and t. So two relatively prime numbers, you can always write as plus, you can always find s and t such that as plus bt is equal to 1. But now what happens, as is in the set because it's a multiple of a. bt is also in the set, so because it's a multiple of b. That means by closure, as plus bt is in the set. So 1 is in the subgroup generated by a and b. If 1 is in the subgroup generated by a and b, then the subgroup is simply the integer set of integers itself because 1 generates that. So you can't take relatively prime numbers and try to generate a subgroup. It will always end up giving you z. But if you take, for example, 2 and 4 like this, then the subgroup generated by them is simply 2z. If you take 4 and 6, then again the subgroup generated by them is 2z. Because now you see all the things are coming together. Because the by definition of GCD, GCD is the smallest number, positive number that can be written as a multiple of one number plus the multiple of the other number. So see, if you're talking about the set containing all the multiples of 4 and 6 and their sums and whatnot, then obviously the GCD will be part of that. Similar to how if A and B were relatively prime, their GCD was 1 and 1 would be a member of the subgroup generated by A and B. And GCD would be the smallest positive number that can be written as a linear combination of those two numbers A and B. So that would be the smallest positive number in this set itself. And from the previous theorem, the smallest positive number in the subgroup will generate the subgroup for integers. So since GCD of 4 and 6 is 2, the subgroup generated by 4 and 6 is 2 then. Similarly, if you take more than two numbers also, more than two numbers, then you'll have to, then again you have a notion of GCD. GCD is the smallest number that divides all three numbers or four numbers, however many generate numbers you have taken in the set S. Then we haven't shown it, but I think you could show that even in that case, the GCD would be a number that can, the smallest positive number that can be written as multiples, sum of multiples of the elements in the set S. So again, even in that case, it will simply be the subgroup generated by GCD of the elements in that set S. Okay, but if you feel confused in any part, you can rewatch that part and ask me in the next class, no problem. Or if you have understood, then that is also fine. One more interesting example when it comes to the generation is if you consider the set of non-zero complex numbers. And when we say non-zero complex numbers, automatically we are excluding zero because we want to consider multiplication. Otherwise, the entire set of C itself is a group under addition. So in this set of non-zero complex numbers under multiplication, the subgroup generated by 1 and I, what is it? Here this is under multiplication. So there are no multiples and there is no addition. There are only powers and product of powers. You just have to get used to it by solving examples. So what will be the subgroups generated by 1 and I? No, it does not. It doesn't. One and I can't generate complex numbers under multiplication. See, that's all. Yes, it is under multiplication. So you can only take the powers and products. Yes, so you don't get multiples of 1 and I. You get powers and products of 1 and I. Yes, it's just 1. I and minus 1, I cube is I times I square times I, which is minus I. Yeah, so that's all you get in under multiplication. But this is also generated by I itself. Yeah. So just because you write two different sets, so the subgroup generated by two different sets can be the same. S1 not equal to S2, S sets does not mean that the subgroup generated by S1 is not equal to subgroup generated by S2. Okay, that's not very important. Just an example. The important next important concept is the there are two subgroups. Now this was one subgroup, the subgroup generated by an element. You don't really have to worry too much about the subgroup generated by a set. Anyway, it's just the multiples of all the elements in the set uh, if it's under addition, and then you can add the multiples of different elements also. But that we will not see that too much. What is important is the subgroup generated by one element, which is simply the powers of the element under multiplication or multiples of the element under addition. That is one kind of important subgroup. Next subgroup you might come across is the the center of a group. Of course, while defining it, we won't really bother about whether it is a subgroup or not, but it turns out that the center is a subgroup. The center Z of G of a group G. So the Z is from the German word Zentrum or something, which means center, subset of elements in G that commute with every element of G. In symbols, Z of G is A in G such that AX equals XA for all X in G. Okay, for this and the next subgroup, I can't give you proper example because the proper interesting examples come from dihedral groups that we didn't look into too much. So you just have to stick with the definition. The definition is clear, right? We say that two elements commute if AB is equal to BA. 2 plus 3 is 3 plus 2, so 2 and 3 commute. In integers, all elements commute with all other elements. So if you take any integer A and any other integer B, A plus B is equal to B plus A. Because it is an abelian group. But it is possible that only some of the elements in a set commute and some elements don't. Yeah, for that I will have to give example in the dihedral group. Uh, at least I can just tell it to you. How much you understand is up to you. We had D4, the symmetries of the square, right? So the There was a 0 degree rotation, 90 degree rotation, 180 degree rotation, and 270 degree rotation of the square. Then we had the horizontal flip, the vertical flip, flip across the diagonal, main diagonal, and flip across the other diagonal. Now in this group, in of course, in any group, the identity commutes with all the elements, right? So E times A is equal to A times E is equal to A. This part is not necessary, but E times A is equal to A times E for all A in G. So E belongs to the center ZL. Now that is not the only element in this group. This R180 will commute with every other element. So R180 times R0 is equal to R0 times R180. You write down the table for this. R180 times R90 is equal to R90 times R180. It is easy for rotations because if you rotate by 0 and then rotate by 180 degrees, that's the same as rotating a plane figure by 180 and then rotating by 0. So totally you will be rotating by the sum of the two numbers anyway. So rotation by 90 and then rotation by 180 is simply rotation by 270. Which you can also get by first rotating by 180 and then by 90. So it's not very surprising that the rotations all commute with other rotation. But only for R180, the reflection also commutes. R180H is equal to H times R180. See, you have the square with four corners A, B, C, D. You put that square, you take a square, right, and then you write A, B, C, D on both sides of the. You take one square sheet, write A, B, C, D in the same place on both sides of the paper. Okay. Then when you flip over that paper, also there will be A, B, C, D written on the opposite side, such that the same corner has A. So if A is in this position, then behind, exactly behind that, you should still write A. If B is in this position, top right corner of the top, then behind that also you should write B. Okay. Then a rotation by 90 degrees is simply moving the positions by one place. If you rotate it like this, then the A, B, C, D all moved by one position to the left counterclockwise. This you can get by rotating the entire square along an axis that is perpendicular to the center. So to the center of the square, you poke a piece of wire or a stick through it, and then spin the stick like you would spin a top. If you rotate it by 90 degrees, then this is what you will get. You rotate it again by another 90 degrees, then you have moved the position of A twice in the counterclockwise direction. So this is actually A, B, C, D. This is R180. Okay, even if you can't visualize this, just understand that R180 is the operation of moving each letter counterclockwise by two positions. That much is you can understand, right? Forget about the visualization. Then by H, what I mean is I'll copy it down here. So H is a flip about the vertical axis, the horizontal axis. So what you do is you have A, B, C, D, and you interchange the letters that are on the opposite side of the horizontal line. So you'll interchange C and B, you'll interchange A and D, right? You're sort of reflecting along this axis from here to here and reflecting from here to here. So you will interest in, we don't forget, if you forget about the visuals, what we are doing is we are simply interchanging the letters on the right side. The top will come to top right letter will come to the bottom right, and the bottom right letter will go to top right. Similarly, on the left side, the top letter will come below and the bottom letter will go up. That is the operation H. Okay, is that fine? No, this is still R180 and RH I have defined now. Now I have to show that it is commutative, right? I have still not shown that. Huh. Yes, that's what it means. If it is abelian, the center of the group is just a group. If it is not abelian, then in the extreme case, the center can contain only the identity. Only the identity element has this property that E times A is equal to A times C. And all the other elements don't have this. But in some cases, there might be an element other than, there might be many elements other than the identity also that have this property. So here, if I do R180 first and then H, what will happen? I did R180 first and then I'll do H on the figure. So by H, what I should do is I should interchange the corners on the same side. So on the right side, I have C at the top and B at the bottom. I will interchange that, B, C. The left side, I have D at the top and A at the bottom. I will interchange that. This will become A, D, B, C. This is what it will become, right? Now, below I have already done H. I will do a 180. What is 180? Move all the letters counterclockwise by 2 positions. So this D is here, it will move to this position. D will go here. Then C will go to this position. C will be here. Then B will go here. Then A will go here. That's just by definition of R1. Now you can see that both are the same, right? After doing both operations, whether I did R180 first and then I did H, or whether I did H first and then did R180, you will end up with all the letters in the same position. And this property is held only by the operation R180 in this actually in any group, in any dihedral group. I can simply write that as the example. For we only have dihedral groups for n greater than or equal to 3. The center of the group Z of Dn is R0 is the identity, it will always be in the center of the group. Otherwise, R180 is the only possible candidate. But R180 is an element of the group only when n is even. Otherwise, R180 won't exist in the group. So, in the case when n is odd, only R0 is in the center. That completely characterizes the center of every dihedral group. So, that is the center of a group. And next, um, this center is a subgroup. How do we show that? E belongs to Z of G for any G, right? So Z of G is non-empty. The identity element is always in the center because E times any element in the group is equal to that. E times A is equal to A times E for all A in the group. Suppose A and B belong to the center of the group. What does that mean? By definition, for all X in G, AX is equal to XA and BX is equal to XB. To show what we have to show, AB is in Z of G and A inverse is in Z of G. That is, for all X in G, ABX is equal to X times AB and A inverse X is equal to XA inverse. That's what we have to show. Now consider AB times X. This is A times BX by associativity. This is A times XB. Because BX is equal to XB, since B is in the center. By associative again, this is AX times B. But AX is equal to XA since A is in the center. So this is equal to XA times. By associativity again, this is X times A. So A has the property that for all X in G, AX is equal to XA. And B has the property that for all X in G, BX is equal to XB. Then AB also has the property that for all X in G, AB times X is equal to X times AB. Now to show this property for inverse, since AX is equal to XA for all X in G and A in the center G, center zero G, you can multiply on the left by A inverse. A inverse AX is equal to A inverse times XA This implies that A inverse A times X is equal to A inverse X times A. But A inverse A times X is nothing but A inverse A is identity E. E times X is X. So this X is equal to A inverse X times A. Then you multiply on the right by A inverse. Get X A inverse is equal to A inverse X times A inverse, which is nothing but A inverse X. So we showed that if AX is equal to XA, then A inverse X is equal to XA inverse. So A inverse belongs to Z of G. Thus Z of G is a subgroup of G. So here you can see that if there is only R0 in the group, that is just the identity element, it is a subgroup. And you can see that R0 R180 is also a subgroup because um, R0 times R180 is equal to R180 times R0 is equal to R180. R0 times R0 is equal to R0. So um, closure in those cases is fine. And R180 times R180 will be R360, which is equal to R0. So closure is followed and it's a finite subset. So R0, R180 is a subgroup of DN. And we'll end with a small definition, another subgroup, and prove that it is a subgroup. Centralizer of A in G. So let A be a fixed element of a group G. The centralizer of A in G, which is denoted by C of A, is the following set. C of A is set of all elements in the group that commute with A. So all those elements G such that GA is equal to AG. Here A is fixed. This is defined for one element A. And centralizer is a subgroup. Uh, no, they will. We can't really say that. What you can say is the centralizer is a subset of the center for every element A. Because if some element belongs to the center, it commutes with all elements in the group. So since A is an element of the group, it also commutes with A. So any element in the center will be an element of C of A for all A. So the center is a subset of the centralizer for every element A. I'm not sure if I said it the other way around the first time, but Center is a smaller set. It is the subset of C of A. Then you could say then C of then you could say from C of A you can find out Z of G, but you'll have to take the intersection. Then, that's all. So the intersection of all C of A's would give you the center. Is that clear? Yeah, C of A is a subgroup. Proof is easy. Uh, E times A is equal to A times E. So E belongs to C of A. C of A is all the elements that commute with A. If XY belong to C of A, then by definition that means XA is equal to AX and YA is equal to AY. To show XY times A is equal to A times XY and X inverse times A is equal to A times X inverse. That is the if X and Y commute with A separately, then their product XY commutes with A and the inverse of X commutes with A. This is simple because XY times A is X times YA, which is X times AY, is XA times Y, is A times X times Y, is A times XY. So that's the first condition. And if AX equals XA, then AX X inverse equals XA X inverse, which implies A is equal to XA X inverse. Multiply on the left by X inverse A is X inverse X times, sorry, this was, which is nothing but AX. So C of A is a subgroup of C. Okay, I'll try to see if there are some better examples for centralizer and center of a subgroup, but at least try to uh, understand the definition, make sure that you are clear on what it means. Because both are similar, but they're actually very different. I can do, I wanted to do a bit of cyclic groups, but I can also skip that and go to homomorphism. What do you want? Okay. All right, we'll move on to homomorphisms. And if we need any of the results from the cyclic groups, then for in any of the later lectures, then I'll come back to it and prove the result that I need. Okay, that's it for today's lecture. Good night.